So hello everyone, this is Dr. Nimish Kumar, and in this lecture series of optical communication, that is KEC 058 code. So we have already discussed what is the LED and what is the laser source, and so in this we have discussed all the phenomena related to LEDs and some phenomena related to a laser. And in our last class we have discussed about the Fabry-Perot laser. We have built the basic concept related to a Fabry-Perot, how that structure can be framed. Apart from that, now in this video lecture we will discuss about the remaining lasers, that is the distributed feedback laser and the vertical cavity surface emitting laser diode also, and we will see all these things in details. So in our last class we were supposed to start with the distributed feedback laser. So what is happening in the distributed feedback laser? We are providing a variation, we are creating a variation in the refractive index just near the surface of the active layer. So that periodic variation, that perturbation in the refractive index is something called as a grating. So what is happening in the distributed feedback lasers? The optical resonator or the optical resonator structure is due to the incorporation of a Bragg grating, or which is also called as a periodic variation of the refractive index into the multi-layer structure along the length of the diode. So this is the variation in the refractive index, which we can see from this graph, this variation. So this is the variation in the refractive index. So we are creating this variation in the refractive index of the refractive index profile along the length of the diode, so that whenever a light is moving into this layer, they will be reflected back by this grating, and as a result which will reduce the losses that is occurring inside the laser. So the fabrication of this device, that is distributed feedback laser, is almost similar to the Fabry-Perot types. The difference is that the lasing action is obtained from the Bragg reflectors, which is also called as a gratings, or the periodic variation of the refractive index, and which are incorporated into the multi-layer structure along the length of the diode. So in general, what is happening? The full optical output is needed only from the front facet of the laser. That is the one which is aligned with the optical fiber. So in this case, a dielectric reflector can be deposited on the rear laser facet to reduce the optical losses in the cavity, to reduce the threshold current density, and also to increase the external quantum efficiency. So the reflectivities of this type of a laser is greater than the 98%, which can be easily achieved with the help of a 6-layer reflectors. So now for the high speed long distance communication. In order to have a high speed long distance communication, we need a single mode lasers, a laser which can be efficiently coupled in the single mode fibers. So we need this kind of situations. We have to build this single mode lasers which can be efficiently coupled in the single mode fibers for a high distance or high speed communication for the longer distance. So we can attain this only with a single longitudinal mode and a single transverse mode. If there are a multiple longitudinal and a multiple transverse mode, then we cannot achieve this requirement. So consequently, what is happening? The spectral width of the optical emission is very narrow, because we are having the only one longitudinal as well as the transverse mode. So the spectral width will be very narrow. So and if the spectral width is narrow, it is highly efficient way of coupling the light emitted from the laser into the single mode fiber for a long distance as well as for a high speed. So the one way of restricting a laser to have only one longitudinal mode is to reduce the length L of the lasing cavity of the point where the frequency separation del f of the adjacent modes which can be given by the formula, which is del V or del nu equals to C by 2L NL, where L is the length, or we can say that L is the length of the grating. So what is happening is, if the del nu, that is that the separation between the frequency is larger than the lasing transmission line width, so that is the only then we get only a single longitudinal mode which fall within the gain bandwidth of the device. So for an example, if we take an example, Fabry-Perot cavity, all longitudinal modes which have a nearly equal losses, and they are spaced by about 1 nanometer in a 250 long cavity at 1300 nanometer. So by reducing that length of the cavity from 250 to 25 the modes spacing increases from 1 nanometer to a 10 nanometer. So however, this length make the device hard to handle, and they are limited to optical output powers of only few milliwatts. Now, so because of that restrictions, there is a need which can give, there is a need of developing a laser which can efficiently emit the light, which can efficiently emit the optical signals, and which can be very efficiently coupled with the single modes fibers. So what is happening among these, in the vertical cavity surface emitting laser diode, the idea behind the development of this kind of a laser is that the vertical cavity surface emitting lasers structure have they have a built-in frequency selective grating and tunables, and they are tunable lasers. The most attractive point of this vertical cavity surface emitting laser is that light is emitting perpendicular to the surface, which can be easily shown in the next figure we will see. And this feature of light emitting perpendicular to the surface, they will help us in the integration of multiple lasers into a single chip, or onto a single chip in one-dimensional or two-dimensional arrays. So because of this one most important advantage, that is the light is emitting perpendicular to the semiconductor surface, which will help us in integration of multiple lasers onto a single chip in one dimension or in a two-dimensional. And because of this this make them attractive for wavelength division multiplexing applications. So because of this, they are highly attractive in the application of wavelength division multiplexing. Now the active region volume of these device is very small, which leads to a very less threshold current, generally less than 100 milliampere. Apart from that, for an equivalent output power compared to the edge emitting lasers, the modulation bandwidths are much greater, and since the higher photon density reduce radiative lifetime. Now this is the figure for the vertical cavity surface emitting laser diode. As one can see that from here figure, that light is emitting perpendicular to the surface of the semiconductors. So with this we can efficiently couple the output light with a cable, which is the optical fiber. So that's why it is used in a high distance, high speed communications. So this the mirror system used in the vertical cavity surface emitting lasers, why mirrors are used? To form the resonant cavity, which is very important for getting the resonant frequencies, and since the maximum reflectivity is needed for the efficient operations. In this figure we can see that one mirror system, this one, that consists of a semiconductor material such as silicon or silicon dioxide as one material, and the other oxide layer such as silicon and and Al2O3, right, as the other material. So these materials can be used in the fabrication of the vertical cavity surface emitting laser diode. So till now we have discussed the different types of a laser, and among them we have seen that the most efficient form of a laser is your vertical cavity surface emitting laser diode. Now, this concept is an important topic related to the unit and related to the optical communication is, once we got the information about all the sources, laser as well as the LEDs, we got that which one is more of coupling the light. Obviously it is a laser because it is highly coherent, and the light emitted from a highly coherent laser source will be highly directive, and if it is highly directive means that most of the information will travel through the optical fiber, because we are coupling this information into the optical fiber. So whatever the fiber fly lead is there, that will be directly connected to the source and with the fiber. So this laser, which is having a spectral width of around 1 nanometer, that is very good attractive point related to the that means related to the way in which we can couple the optical signal into the optical fiber, because we have seen the very first important requirement for a source to be a good source is that it should be having a very narrow spectral width, because this narrow spectral width can be efficiently coupled into the fiber, especially into the single mode fiber, which can be used for a long distance, which can be used for a high speed communications. Now we are going to discuss about the receiver part. So in that receiver part, before moving into the photodetectors, what are the types of photodetectors, what is the phenomenon which is responsible for detecting the optical signals, we will first try to build see the basic concept to the receiver, like power budgeting. This terms most of the students related to a communication background, they might have heard this word, that is power budgeting. So the same thing is used in the optical course also, optical communication also. In this, what is the need of this power budgeting? This need of power budgeting is to find a safer distance that can be used for a optical fiber, right? If suppose that I have to transmit information to a 2000 kilometer, so that 2000 kilometer must be having a multiple fibers, and that multiple fibers, they must be having some losses, right? And that losses adding up inside the signals, inside the optical wavelength, and they will reduce the strength of the information. So what is the safer distance between the two fibers without the use of a regenerators? The basic idea is to find a safer distance at which we can use the regenerators. Like suppose that after calculating the power budget, we found that this is the amount of a power that is available at a distance of 100 kilometer. Suppose that the strength of that signal is just above the safer level. So, and the moment we are moving to 150 kilometer or 110 kilometer, definitely that signal strength will further reduced to a critical value, to a threshold below the threshold value, which can be easily detected by the receiver. So at that point we need a regenerators that can regenerate back are the original signals, right? So the idea of a power budgeting is to find the distance after which we have to use the repeaters or regenerators to regenerate our original signal back. So this is the basic phenomena. This is the basic phenomena that is responsible for calculating the safer distance of the fiber. So in this, what we are going to do, we are first going to see this figure. This figure has been directly taken from the Gerd Kaiser. It's the optical fiber communication book. One can easily refer to that book in order to get in details about each and every points related to this figure. We will very briefly try to understand, try to encapsulate all those contents in some nutshell points, and we will try to form the formula for the power budget. So in this, what we are seeing, that we are having a transmitter and the receiver, and between transmitter and receiver there are various fibers, they are connectors, they are splices, right? So what is happening, whenever a light is emitting from the laser source, it is going to be coupled inside the fiber. It is coupling, moving inside the fiber. Now this is a fiber fly lead. What is fiber fly lead? If we want to connect the optical signal into the fiber, we need a fiber fly lead, right? If we are not using the fiber fly lead, then what is happening? You have to very efficiently couple that light into the fiber, because somehow there might be a mismatching between the points from which your optical power is coming, and there will be a mismatch between that optical power point of emission and the core diameter, right? There might be possible that even though you assume that your fiber core is within that point of emission, but somehow unintentionally that fiber core might have moved upward. So that means most of the optical signal not going to couple inside the optical fiber. So in order to efficiently couple that optical wavelengths into the fiber, we need a fiber fly lead. What is happening in the fiber fly lead? There are some connectors which are internally there at the output side. We are having a connectors. This connector are internally connected inside the optical source during the fabrication process. During the fabrication process, we are already providing an internal connection of this connectors with the optical source. That means there will be some fibers which will be internally connected through the optical source. So the moment light is emitted, they will move directly into the fibers. Now at this output side, we are connecting the fibers. Suppose we have to transmit an information to a distance of 500 kilometer. So obviously we can't lay down the 500 kilometer fiber in a single movement, right? So for that, for providing a 500 kilometer connections, we need a various fiber spools, because we are having a spools of some standard length. That is, suppose that if a standard length of a fiber spool is, suppose that it is a 10 kilometer or a 15 kilometer, then in order to cover that range of a 500 kilometer, we need a multiple fiber spools, and these multiple fiber spools, fiber end have to be joined in order to couple that light. So that is something done here, that is fiber spools are joined by a process called as a splicing. So one thing, we have connected the fibers with the source at this point with the help of a connectors, and after that there will be a multiple splices to get the required length. And suppose that before providing the connection with the receiver, you want to do some test. What is the test? You want to know what is the strength of the wave, what is the strength of the optical signal, or what is the wavelength that is coming inside, right? So all these things can be performed. You want to do some testing, you need some test equipments. So your fiber should be connected with the test equipments. So for that we need a connectors whose other end will be directly connected to a testing devices, will be connected to the testing devices. So now if you want, then you can use it. If you don't want to investigate the various the optical signals, then avoid this part and you can directly connect with the receiver.